Artificial intelligence is expanding its reach. Code that previously generated digital text and images is now being written to physically manipulate atoms in the real world. But executing that code on physical hardware presents an immediate, catastrophic problem. When a digital algorithm attempts to move a robotic arm without mathematically accounting for real-world friction and mass, the system violently fails. The industry faces a severe shortage of engineers trained to account for these physical constraints within their code. Most degree programs keep physics, mathematics, and computer science in separate buildings, leaving the interaction between them untaught. Operating within the economy of atoms requires an educational architecture built for integrated systems thinking. 3D simulation serves as the connective tissue required to link these disparate disciplines together. This diagram outlines a 4-tier workforce pipeline, spanning from secondary school through advanced academic research. The entire structure is interdependent. Each tier relies on the foundational frameworks and outputs established by the level beneath it. Deploying safe, functional physical AI at scale requires treating curriculum design as a rigid systems engineering problem. At the baseline tier, secondary education moves away from purely theoretical physics and isolated coding classes. The curriculum utilizes commercial 3D game engines as interactive physics laboratories. Students write basic scripts to alter variables like gravity and mass, allowing them to instantly observe the physical consequences of their code. Connecting code directly to spatial models introduces the concept of building a digital twin. Computer science modules shift their focus toward AI training, moving beyond the writing of static algorithms. Students learn how to spawn randomized 3D objects to generate the synthetic data necessary to train basic computer vision models. Merging these environments early prevents academic silos from forming, treating code and physics as a single coupled system from the start. The second tier addresses the industry's largest labor gap, the specialized technicians required to operate digital factories. The first essential role is the simulation asset technician, a position that bridges the gap between 3D art and engineering. These technicians master universal scene description formats to lock accurate physical properties directly onto visual meshes. The second critical role is the synthetic data operator, the technician who commands the procedural generation tools. Their primary task relies on domain randomization, the rapid alteration of environmental variables to create robust training datasets. Operators alter lighting, textures, and camera angles around a simulated robot to force the AI to learn spatial adaptability. The capstone of this vocational tier is hardware-in-the-loop testing. This is the hands-on process of taking code that was rigorously tested in simulation and deploying it directly into physical industrial robotics for live diagnostics. Without this vocational deployment engine generating physically accurate assets and synthetic data, advanced AI models have nothing to train on. At the undergraduate level, computer science and mechanical engineering merge into a unified physical AI systems degree. The curriculum moves past large language models to focus on world foundation models. These models are designed to predict physical kinematics and spatial dynamics directly from visual and sensor data. The defining experience of this tier is the Sim-to-Real engineering lab, where an AI is trained in simulation and then deployed in reality. This split-screen chart illustrates their primary adversary, unmodeled physics, such as sudden wind gusts or unpredictable sensor glare. The mathematical delta between simulated perfection and real-world chaos is defined as the sim-to-real gap. The tertiary tier produces polymaths, whose entire skill set is dedicated to anticipating and erasing this exact gap. At the apex of the pyramid, encompassing master's, PhD, and postdoc research, the focus moves to deep physical constraints and AI autonomy. This tier focuses on agentic simulation workflows. Researchers design multi-agent systems where AI autonomously writes the code and generates the 3D models required to build massive simulations. The human researcher evolves into an orchestrator, tasked solely with evaluating the physical validity of the AI's autonomous work. Researchers close the hardest gaps by integrating thermodynamics and quantum mechanics into real-time simulators for high-stakes surgical robotics. This level also introduces the ultimate research priority, ethics, and bounded physical AI. Engineers write rigorous mathematical proofs that guarantee a robot cannot violate safety parameters in the real world, regardless of how it was trained in simulation. These mathematical guardrails are the prerequisite for society to safely adopt autonomous physical machines in our hospitals, cities, and homes. Isolated software engineers writing algorithms in a vacuum cannot scale the economy of atoms. Success relies on a fully synchronized systemic workforce pipeline operating in unison. The active pipeline functions as a single circuit, with vocational assets flowing upward and advanced safety proofs cascading downward. Synthetic data produced vocationally directly powers undergraduate sim-to-real laboratories. In return, advanced PhD research distills into foundational game engine tools for secondary students. 3D simulation serves as the universal language across all of these disparate educational levels. Bridging the gap between digital code and physical reality is a human curriculum problem, and this 4-tier framework provides the blueprint to solve it.